Hi, it's Sukrit from STEM Coder, and in today's video we're going to look at the concept of concavity. So over here I have three functions on these three graphs. First, let's go ahead and try to draw the derivative of these three functions. Of course, we don't actually know the definition of these functions, so we're going to try approximating the derivative. So let's look at this function over here. Clearly at this point the function is sloping downwards, and as you get closer to this point the downward slope decreases. So it's sloping downwards a lot, then sloping downwards a little, then it's barely sloping downwards, and at this point the function is completely flat, right? And after that it slopes up a bit, then slopes up a bit more, and by this point the upward slope is steep. So clearly the derivative starts from being negative, which means sloping down steeply, and becomes more positive over time. So the derivative should look something like this. You can see initially the derivative is really negative. At this point over here, when x is equal to whatever this is when the derivative is equal to 0. It's when the function is completely flat. And after that, the derivative becomes positive. Now let's take a look at this function over here. It's similar to this function, except it's the opposite. Initially, the derivative is sloping upwards, then it becomes flat, and then it's sloping downwards. So the derivative actually starts out as positive somewhere here. So I guess the derivative will start out as positive somewhere here. It'll keep going down, and when x is equal to this is when the derivative is equal to 0, and then the derivative keeps decreasing from then on. Now I'm going to leave the third function alone for now. Let's just focus on these two functions. So clearly for the first function the derivative keeps increasing, and for the second function the derivative keeps decreasing. Now we also want to take the second derivative of these functions, and remember the second derivative is just the derivative of the derivative of the function. And with this function we can pretty much say that the derivative is almost constant, and it looks like just a straight line, and it's always positive. This line is always pointing upwards, it's always increasing, so the second derivative will look something like this. Maybe just a flat line somewhere over here, because this derivative is always increasing, so the second derivative is always positive. And this line is a different story. The derivative of this function over here, so the second derivative of this function is the derivative of this function. Well, that's all. Second derivative is always going to be negative, right? Because the derivative of this function is always decreasing. So the derivative of this function has a negative derivative, and so the second derivative is always negative. That makes sense, right? Well, why I wanted you to understand these concepts well was for this third function over here, because it exhibits some interesting behavior. Let's start out with the derivative. So initially at this point the derivative is steeply positive, right? So initially the derivative is pointing upwards, it's pretty steep, and as you approach this point over here the derivative becomes less and less steep, so it becomes more and more flat, but it doesn't quite become perfectly flat. But at this point something happens. The derivative is decreasing until it hits this point, and then it begins increasing. So from this point the derivative again goes up, it gets larger, it gets even larger. So we have a derivative which is decreasing, and then a derivative which is increasing, but the derivative is still always positive. So what do you think that'll look like? Well, maybe it'll look like this, a parabola. And you see why? Initially the derivative is steeply positive, so derivative is steeply positive, and then it keeps decreasing until the derivative stops decreasing, and then the derivative starts increasing from that point. So it looks a lot like a parabola, right? Well, then if the first derivative looks like this, what do you think the second derivative looks like? Well, based on these functions, second derivative should actually look like this. Why? Yeah, so do you see why this graph is like this? Because initially the derivative is decreasing. So you have like a high derivative, it keeps decreasing until it reaches this point, after which it keeps increasing. And that's kind of what's going on over here. If you look at the slope of the derivative, initially it's pointing downwards, and then it points upwards. So that's why the second derivative function looks kind of like that. So I said this video is going to be about concavity, right? Well, that's exactly what we're going to learn right now. If the second derivative of a function is negative, like this, or where at least the second derivative of a function is negative, it's called concave down. So this is called concave down. Why? Because the second derivative of the function is negative. The derivative is initially positive and it just keeps decreasing after that point. So the derivative is decreasing. let's look at this function. The derivative is increasing. Initially the derivative is negative, then the derivative is 0, and then the derivative is positive. So the derivative is constantly increasing, and if that's the case, well then this is concave up. So this is concave up because the derivative is increasing. This is concave down because the derivative is decreasing. You can think of concave up as an open bowl, concave down as an upside down bowl. What about this function over here? Well, from here to here, the derivative is decreasing, right? Because initially it's really steep, then it becomes less steep. But what about from here? Well, then the derivative starts increasing again. So the function is actually concave down over here and concave up over here. This is an interesting phenomena. We see that it's concave down, like you can see that it looks like an upside down bowl over here, but over here it's concave up. See, it's getting steeper, it looks like a right side up bowl. And this point over here, where the concavity changes from down to up, that is called the inflection point. The inflection point is basically where the concavity changes from down. We call concave down as negative concavity to concave up, positive concavity, and where the concavity changes the direction, that's the inflection point. And remember, inflection point doesn't just have to look like this. An inflection point can also look like this. It can look like this. You can see it's going from one concavity to another. It can look like this. Once again, it's going from one concavity to another. There's a lot of ways you can draw inflection points. But basically, the inflection point is where the concavity of a function changes. And the concavity of a function is defined by the sign of its second derivative. So over here, this is because there's a positive second derivative. And it's concave down because there's a negative second derivative. Yep, and that's all there is to concavity in a nutshell. I hope you found this video helpful, and I look forward to seeing you in future lessons.